It's a pleasure to introduce Professora Marisa Gutierrez from Universidad de La Plata, Argentina. Professora Marisa had the first contact with Brazilian researchers when she met Claudio Leonardo Lucchesi in La Plata when he was visiting another researcher. And then she started an intense collaboration with Universidade de Campinas, especially with Professor João Meidanes. And the Carioca community of Cliques and Graphs had the first contact with Professora Marisa, if I'm not wrong, in 1996. In a workshop of combinatorics, we organized it in Universidade Federal do Rio de Janeiro. And so we are talking about 22 years of collaboration and friendship. And since that time, Marisa has frequently come to Rio de Janeiro, and many Brazilians have visited La Plata as well, including myself. Marisa has very important contributions in the field of click graphs. She's one of the authors of the important and nice paper on the complexity of recognizing click graphs. And this problem remained open for many years and was finally proved to be NP complete by Marisa and other authors that are present here. She has also important contributions in studies of classes of graphs, in chordal graphs, results on chordal graphs, dually chordal graphs, APT graphs, interval and proper interval graphs, click-Helly graphs, and many other classes. The extension of Marisa's work can be measured by the positive impact of the excellent team of researchers advised by her. For instance, Liliana Alcon, Silvia Tondato, Pablo De Caria, Patricia Dobson, and others. And so it's an honor and a pleasure to have her again with us, and she's going to talk about click operators in digraphs.
Well, thank you for all. Thank you for Fabio to your kind words. And thank you for the organizer for inviting me to this nice event. And well, I choose to talk about click operators because the meeting is called Latin American Workshop on Clicks in Graphs. And this is because this thing has a history. Then my talk is, first is in cooperation with Silvia Tondato from my university, Guadalupe Sánchez Valdupi, also from my university, Bernardo Llano and Miguel Pisaña from the University Autónoma Metropolitana of Iztapalapa de Mexico. And the talk is divided in the following parts. First, a history part about the click operator in graph, something about the imagine, the behavior in classes, the iterating clicker operator, the divergency. Following this, I introduce new operators, but in digraphs. Die-clicker operator in digraph is a joint work with Bernardo Llano, Miguel Pisaña, and Silvia Tondato. The definition, the imagine, the properties, behavior in classes, iterating the click operator, divergency. And in the last part, I will talk about the transitive tournament operator, that is another operator in digraph, the definition, the relations with other operators in the behavior in classes. This part of the talk is together with Bernardo Llano and Guadalupe Sánchez Valdubi. But no click operator a talk can be started without the definition of the click operator. What is a complete of a graph? A complete of a graph is a set of vertices such that they are pairwise adjacent. But what is the click of a graph? A click of a graph is a maximal complete of the graph. In this example, I have 4 clicks, 1, 2, and 3, 2, 3, 4, and 5, 4, 5, 6, and 3, 5, 7. 4 clicks. But what is the click operator? The click operator takes to each click as a vertex, and 2 clicks are adjacent if and only if they intersect. In other words, is the intersection graph of the clicks of the graph. This graph is called, this graph is called, it's possible to, it's not possible. Sorry. Oh. I think something wrong. But I don't know how is to. No, quiero apuntar. Is this. This graph is called the click graph of this graph. This is a click graph. But what happened with the click graph? The first question appears some years ago is about the imagine of the click operator. All the graphs are click graphs, in other words, are in the imagine of the click operator. Hamelin said no, and gives a sufficient condition to decide if the graph is a click graph or not. Hamelin said that, I must tell you about the Heli property. What is the Heli property? All the world know what is the Heli property. It's a property of the family of graphs, of sets, sorry. If you have a family of sets, this family has the Heli property if every intersecting family of has non-empty intersection. In the picture you can see we have 3 sets, and this is not empty, non-empty, and non-empty, then the total intersection is non-empty. This is the Heli property. Then Hamelin said that if the click family of the graph has the Heli property, then sure the graph is in the imagine of the click operator. This is the paper, it's very old. But what happened? We have all the graph, the imagine of all the graph are the graph in the imagine of the click operator. The click Heli graph are contained in the imagine, but this graph, Hamelin proved that this graph is not in the imagine of the click operator. The second result, important result about the imagine is devoted to Robert and Spencer that gave the first characterization of the imagine of the click operator, and say that a graph is a click graph if and only if there is a Heli covering of the edges of the graph. And this is the paper, it's very old. And we can see in the picture, this is a graph in the imagine. Observe that the clicks of the graph doesn't has the Heli property, but this graph has that we call a Heli covering. Is a set of completes of the graph that covers all the edges of the graph, but has the Heli property. If the graph has this property, then the graph is in the imagine of the click operator, if and only if. But what happened with the complexity? Deciding if a graph is a clique graph or not is a hard problem. We prove that the problem is NP-complete. Reducing to the satisfiability problem is a joint work with Liliana Alcón, Loerbio Faria, and Celina Figueiredo. What happened with the behavior in classes? There are a lot of papers talking about the behavior in classes about the clique operator. We select some special classes, but there are a lot of papers about this. For example, the clique operator takes the class of clique-Heli graph, that is the class of graphs with the Heli property in the family of the maximal cliques, and the imagine of this class is the class of clique-Heli graph. It was proved by Escalante. The imagine of this Heli is the disk-Heli family, and this Heli is the class of graph that has the property that the disk of the graph has the Heli property. The imagine of chordal graph is the class of dually chordal graph. It was proved simultaneously by so many authors. And the imagine of dually chordal graph is chordal intersection clique-Heli. The imagine of DB graph is dually DB, and the imagine of RDB is dually RDB, is in the same authors. The imagine of Heli circular R is circular clique, Duran and Lin. The imagine of DE is dually DE, and and the imagine of dually DE is DE. So many of these results are compacted in a theory of operators showing by João Meidanes and me and myself in a paper where we study the following. If you take a family of sets, you can see the intersection of this family, the class of graph that is the intersection of this family, or you can take the two sections of this family. It's in this way. Suppose that you take a family of intervals in the line. Then you can do the intersection of this family is a graph of intervals, or you can do the two sections of these intervals. That is, what is the two sections? Is take this family of sets and make all the vertices inside each set adjacent. And we prove that over some properties, K alternates between intersection of the family and two section and intersection. This is our paper in the anniversary of Jaime so many years ago in the first clique meeting. And to say something in the end is about the iterating of the clique operator. This is a part studied by Mexican researchers, is the following. You take the graph, you take the clique operator, and the clique operator anytime, and the clique operator anytime, and the clique operator anytime, and what happened with this iteration of the operator? Maybe you can thought that all the graph converge to a point, to a vertex, but this is not true. This is not true. In other words, is the limit of Kn of the graph, the number of vertices, exactly 1? This is not true, and Victor Neumann gives the first example of a graph that really divergent. Is the famous octahedron. This beautiful graph has the property that has 6 vertices and 8 cliques, so many cliques. And he proves that K of the, observe that this graph is the complement, of 3 edges. And Victor proves that k of the complement of 3 edges is the complement of 4 edges. And in general, k of ON, that the octahedron of n dimension, is the octahedron of dimension 2 up to n less 1. This is the reason because the octahedron divergence. Okay. This appears also in a paper of Escalante and a paper of Victor. It's something simultaneously. But what happened with the divergency? Imagine that this graph divergence. How we construct new graph that divergence? Maybe this graph divergence alone is the only, but it's not in this way. One thing that you can thought is if you put this graph inside another graph, this obligates to the bigger graph to divergence, but it's not in this way. It's more complicated. For example, if you put the octahedron and one universal vertex, one vertex adjacent to all the vertices of the octahedron, then the imagine of this from to the k operator is exactly k8 because all the cliques are adjacent. Do you understand? Yes? And the imagine of k8 is a point. Then the octahedron with an universal vertex converges. This happens with any divergence graph. If I put a graph that diverges inside a new graph, a bigger graph, that the difference is an universal vertex, then the new graph converges to a point. This is very clear. This is the reason because Victor developed the beautiful idea of retractions. What is a retraction? A retraction is a bit difficult to understand in the few words. It's an homomorphism from the graph, the bigger graph G to the smaller graph H, such that, well, an homomorphism, do you know what is this? It's a function that sends vertices of the graph G to vertices of the graph H, such that the imagine of adjacent are equal or adjacent. But what is a retraction? It's an homomorphism such that there is another homomorphism from the smaller graph to the bigger graph, such that the composition is the identity of the smaller graph. And he proved that if phi is a retraction from G to to H, from the bigger graph to the smaller graph, and the smaller graph, there is a retraction also from the k of G to k of H, and he proved that if H diverges, then G diverges. Then this is a machine to construct divergence graphs. Okay? For example, here is our octahedron. All of you know what is a false twin. This vertex, x prime, is a false twin of x. You can see? The octahedron diverges. What happened with the new graph? The new graph is a retraction of the octahedron because I can send the vertex x prime to the vertex x, and all works very nice. Then the new graph diverges. And this is divergence plus false twins divergence. This is a machine to construct divergency. What happened with the periodic graph? What is the periodic of a graph? It's an integer p such that k of p of G is the same graph of G. In other words, the clique operator works, and another time come back to the first graph. This is the first time that this occurs is the periodic of the graph. Escalante proved that if a graph has the Helly property in the cliques, then the periodicity is 1 or 2. But also prove that for every P, there are infinite graphs with period P. This is the paper. Escalante counts as Mexican people. Right, is German, but lived in Mexico, okay? Is Latin American for us. Okay, and to the end, the diameter was developed by Hedman. He proved that the diameter of the graph, with respect to the diameter of K of the graph, is no more bigger than 1 of the difference between the diameter of K of G is not more than 1. Then a graph can diverge in diameter. There are graphs that with this property, that diameter of Kp of G is the diameter of G plus P. But Miguel said that there are only finite sequences of this equality. We don't know if there are a graph that holds this equality for any P. Okay, then this is a new part. The new part is about something similar to this history, but in digraphs. What is a diclic? A diclic, given a digraph D, a diclic, a disimplex, is a pair AB of vertices of D such that A intersection of B is empty. And for every A of A and B of B, there is an arrow from A to B, okay? But what is a diclic or D-click? Is a maximal D-simplex. For example, you can see in this very small example, 2 D graphs, sorry. The first, we have exactly 1 diclic. It's a pair of vertices, a pair of sets of vertices with only arrows from one to the other. This is exactly 1 diclic, and this digraph has exactly 2 diclics. Observe that 1 diclic is superposed with the other. It's not so easy. But what is the diclic operator? You take the diclics of the digraph and construct a new graph whose vertices are the diclics of the D-graph, original D-graph, and such that you put an arrow from a diclic, another diclic, if the second set intersect the second set of the first, intersect the first set of the second, okay? In another example, we can see, for example, in our first digraph is only a diclic, then the imagine is exactly a point. But in this case, we have 2 diclics, the orange and the black. And the imagine is exactly the orange as a vertex, the black as a second vertex, and one is adjacent, there is an arrow from the orange to the black, okay? The imagine of a cycle, a directed cycle, is a directed cycle, at least this. The imagine of a tournament, transitive tournament, do you know what is a transitive tournament? It's like a complete. It's a tournament, it's a complete digraph, transitive. Each time that we have an arrow from this to this, and one from this to this, we have the arrow from this to this, okay? The imagine of this digraph is the digraph, the TT4 is the digraph TT3. Okay, what is the behavior that we observe in the operator? We have digraphs that are self. What is self? The imagine of the digraph is the digraph itself. For example, the cycles. We have examples of digraph that converge to a point. We have. And we have digraph that divergence. But we don't have digraph periodic, at least at this moment. Examples. The imagine of the cycle is the cycle. The imagine of the transitive tournament is the transitive tournament, one less than the first. Then this, for example, this converges. This is self. This converges to a point because the imagine of this is TT2, and the imagine of TT2 is 1 point. What are the ancestors that you can thought about? Marina is here. Marina is here. The ancestor of this operator can sound similar to the Marina B-click operator. This is a very nice paper of Marina, Leandro, and André. Almost every click, every graph is divergent under the click operator. It's beautiful, but it's not our operator. It's very different. It's totally different. Another operator related to our operator is B-click digraph, defined by Prisner in the book Dynamic Graphs, and is similar, but Prisner allowed intersection, allowed loops. I forgot to say that we never consider loops or arrows from a side and the other side, or opposite arrows. But Prisner considered loops and opposite arrows and allowed to intersection between A and B in the sets. What happened with the imagine of our operator? This is like what happened by Prisner. If we take a digraph, for example, this, we put an arrow. Do you remember what is a source or what is a sink of the source, and the sink is the digraph? If the digraph has a source or a sink, you put an arrow through the source from the sink. You do the line digraph of this digraph, and some magic is that the K of this digraph is the former digraph. Then what is the answer about the imagine is that the operator is surjective. Any digraph is the imagine for our operator, is in the imagine. What happened with the die-clicks? We need to prove theorems, we need to develop some tools about the die-clicks. What is the result is the following. Do you know what is n plus of x? Is the set of vertices that follow x. And n less of x is the set of vertices that are back x. What happened with a set? If x is a set of vertices, what is n plus of x? N plus of x is the intersection of all the vertices that follow any vertex of the set x. And the same with n less of x. What we prove? We prove that if we show dx, the set, imagine, you have a set x, you put all the vertices that follow this set and all the vertices that are back this set. This is this formula. M plus x and m less m plus x And this is a D-simplex. And the D-cliques are the maximal of this structure. If you start with the vertex, if you start only with the vertex, we prove that dx, x is a vertex in this moment, you put all the vertices that follow x, only at the vertex x, and all the vertices that are in the intersection of all the vertices that follow x. This is an special diclique called alpha of x. They are very special. And the same if you start with the vertices that are back x. This is called beta dx, but unfortunately, they are not the only dicliques. There are others. But we call Neumann-Lara the digraph whose dicliques are only alpha and beta. Unfortunately, the class of digraph Neumann-Lara are not closed by the diclique operator. For example, this is our digraph. What is alpha of 4? Alpha of 4 is go forward 4 is 1. Go back with 1 is 4. Is 4, 1. 4, 1. Is the same, and beta of 4 is empty because no one goes to 4. What is alpha of 1? Alpha of 1 is goes forward 1, 1, 2, and 2 back, 1, 2, and 1, 3, and go back to with 2 and 3, and this is 1. Then 1, 2, 3 is our diclique, and so on. This digraph, for example, is Neumann-Lara because the only dicliques that appear are the alpha and betas. But in these examples, you can see that the digraph red, 2, 3, 6, and 7 is not an alpha and beta. It's new. It's the catastrophe of the operator. What happened with the adjacencies? If x, there is an arrow from x to I, there is an arrow from alpha of x to alpha of I, and if there is an arrow from x to I, there is an arrow from beta of x to beta of I, but if there is a tournament, this is an equivalent. X goes to I, if and only if alpha of x goes to alpha of I, and with beta is the same. This is the reason because some structures similar to the original graph appear in the imagine of the diclique operator. For example, in our example, what is the imagine of the diclique operator of this graph? Alpha 4, alpha 1, there is an arrow, because here is an arrow, then here is an arrow. Alpha 3 is, beta 3 is not here. Alpha 3 is not here because no one goes from 3. Then alpha 2 is here, but these black arrows are because of this theorem. The new arrow is because appears new arrows from the original graph. We prove that if H is an induced digraph of D, then K of H is a subdigraph of K of D, not induced. We prove that if P is an induced path from X to I in D, then in K of P there is a path between alpha of X to beta of X. The distance between X and I is the distance between alpha of X and beta of I plus 1. And we prove that the neck of the digraph is the same of the neck of the diaclick of the digraph. This is the reason, because if you have a hole in the digraph, this hole is maintained. It's impossible that the digraph converges if it has a hole. It's impossible. Converges to a point. What happened with the behavior in classes? We proved that if a digraph is strongly connected, do you know what is strongly connected? If for every pair of vertices, there is a path, directed path from x to I and from I to x. If D is a strongly connected digraph, it's possible to develop what is the diameter. The diameter is the maximum distance between any pair of vertices. And we prove that if D is strongly connected, K of D is also strongly connected, and the diameter of D is less or equal than the diameter of K of D plus 1, is one of the inequalities that is proved to the click operator, but no, we cannot prove it the other. The behavior in classes, we can tell about the transitive digraph. What is a transitive digraph? It's a digraph such that each time that you have an arrow from X to I and from I to Z, you have an arrow from X to Z. It's transitive. It's like a comparability graph. We prove that, the height of the digraph is the maximum direct path, is the longest path possible not induced in the digraph. We prove that if a digraph is transitive, K of the digraph is transitive also, and the height is less than the height of the digraph original. This is the reason because transitive digraph converge to a point. In a particular case, we prove that the K of the transitive tournament Tn is Tn less 1. What happened? Every I-cycle digraph is a subdigraph of a transitive tournament. Then every I-cycle digraph you can put in a digraph that converges to a point. This is some examples of convergence. These two paths converge to the imagine is this that you can see there. The two cycles, between the two cycles there is two arrows, converge to one arrow. This is another example, In general, this is a sketch. You have a digraph and 3 points, and all the arrows from these 3 points to this, then the imagine is 1 point and all the arrows with K of D. This is the way that you can construct different examples. Other behavior that we observe is in relation with the circulants. If you take a subset of the integers from 1 to n less 1, what is a circulant digraph? Do you know what is a circulant? It's a digraph is very nice, has the vertices, the integers modulo n, and two vertices there is an arrow from I to j, if and only if the difference between j and I modulo n is an s. Then, what happened with R? If you take an R that divides n, you take the coset 1 plus n up to R less 1 and up to R is a non-trivial coset. We prove that the imagine of this digraph is the cycle Cn of R. For example, This is a partially draw of the circulant 12159. This is a coset. This is a partial, because the circulant digraph is the, drawing in this way. You put the first three arrows, and you can imagine that these arrows road circulant. Then the imagine is exactly C4. This is the pilot circulant is C7124, is this digraph. We prove that this digraph diversions only showing what are the diclics of this digraph, because you can imagine that prove that a digraph diversion is very difficult, because you must to develop some tools to are very sure that diversions, or describe all the diclics in any iteration of the operator. It's very difficult. Another example is the digraph H0. H0 is this digraph. It was defined in this paper, and we proved that this digraph also diversions, also describing the diclics. And we developed is very similar to what happened in the Prisoner book, the retraction about the digraph also. And it's possible to prove that this graph, for example, if you put a false twin of 0, this new digraph also diverges. Then the last operator is transitive tournament operator. This is a joint work with Guadalupe and Bernardo. If D is a digraph, what is a tournament of D? Is like a complete. It's a subdigraph, or it's a set of vertices, each one related with the other by an arrow. And what is a transitive tournament? I say before, is with the property that is transitive, no? What is a maximal transitive tournament? Is a transitive tournament maximal in the sense of the inclusion. And what is the operator? The operator takes as vertices all the maximal transitive tournaments, and make two tournaments adjacent, an arrow between one and the other, if and only if the intersection between both transitive tournaments are not empty, but as you know, probably you know, each transitive tournament has a source and a sink. If the source to the one and the sink at the one and the source at the second are in the intersection, but the source to the let me see, because the letters are in Spanish. This is the problem. But in the picture is clear. You have two tournaments. One hand, the source is red, and the sink is red. And one has the source is black, and the sink is black. In the intersection, it must be the sink of the first and the source of the first, but not the others. In this way, you have an arrow. Okay? For example, in this very, very small example, we have what digraph is a path. What are the transitive tournament maximal? an arrow and an arrow. And the two arrows are connected in this way. Then the imagine is that this arrow. Okay? The imagine of the cycle is the cycle. The imagine of, this is interesting. This is a comparability graph. It's the Haas diagram of a comparability graph. Is in other words, in the digraph words, is a transitive digraph. Each click is a maximal path of this digraph, and the imagine is only a digraph without arrows. The imagine of this, we say that a digraph is thin if the only transitive tournaments are the arcs. For example, this is an example. The only transitive tournament are arcs of this digraph. We prove that the imagine of this digraph is this digraph with this operator. It's exactly the line of this digraph. And observe that this digraph, and this occurs all the time. Observe that this digraph divergent one by one. This has 6 vertices, and this has 7 vertices, and the other 8, and so on. We also define what is the spread. The digraph is spread if different tournaments have different sources. And we prove that if the digraph is spread, the transitive tournament applied to the digraph is a sub-digraph of the digraph. This is an example. Well, to end, I think that is, I don't know how do this, but I have a few minutes. I only can show you what happened with the octahedro. If the octahedro, you give orientation to the edges of the octahedro, you obtain so many digraphs. For example, this is the octahedro with an orientation, and with this operator converges to a point. This is the octahedro with another orientation, and we prove that converges to 2 cycles. And this is the octahedro with another orientation, and with this orientation, this orientation diverges. Well, we have so many open problems. I invited you to start to study the new operators in digraphs. Are there digraphs with exponential number of die-clicks? We don't know. Jaime? We don't know. Are there digraphs such that for every n, Kn is Neumann-Lara? We don't know. Are there digraphs with periodicity R, K? We don't know. This is the most beautiful open problem. What happened with SR4? SR4 is this digraph. We are convinced that this digraph diversion is very small, but diversion with the first operator. But we can prove at this moment if this digraph divergence. And I think that Miguel thought, what happened? Miguel thought the last night that convergence, but I don't know. What happened with the Heli property? What happened with the Heli property with coaffinations, expansive digraph in both operators? Are there digraphs with tape periodicity R? We don't know. Some of the bibliography, I can put 100 papers, but it's impossible. We only put the most important. the survey of Jaime about click graphs was very important for this presentation. Thank you. No? Marina? Marina? Orientation. Orientation. Maybe, yes. I never thought in this. I never thought. Mm. I suspect that we can show something relation with the if the diagram the graph that you have is very separated. I don't know. Not maybe we can orient the edges in such a way something happen. But the problem is that you allow to make intersection in any place, and we only allow make intersection between the second set and the first set. This is the difference. Yes.